welcome. All right, so let's watch this little video. It is not super exciting, but it's not horrible. So,
hello. In this video, you'll learn how to write Lewis structures for molecular compounds. The first step in writing the Lewis structure is to write the correct skeletal structure for the molecule. When you write the skeletal structure, you have to put the atoms in the right positions. For example, if you're writing a Lewis structure for water, you put the oxygen in the middle of the two hydrogen atoms, because this is how the atoms actually bond together in nature. You could not write the correct Lewis structure if you put the hydrogen atoms next to each other. How do you determine the correct skeletal structure? Well, the only way to determine it with absolute certainty is to experimentally examine the molecule structure. However, you can write likely skeletal structures by following these two guidelines. First, place hydrogen atoms in terminal positions. Hydrogen does not ordinarily occur as a central atom because central atoms must form at least two bonds. And hydrogen, which has only a single valence electron to share and forms only a duet, can form just one bond. Second, place the more electronegative elements in terminal positions and the less electronegative elements, other than hydrogen, in the central position. For example, suppose you wanted to write a Lewis structure for H2CO, which is formaldehyde. You begin by drawing the skeletal structure. The least electronegative atom is carbon, so place carbon in the center. Place the hydrogens on either side of carbon. Oxygen is more electronegative, so place oxygen in a terminal position. In this case, above or below carbon. The next step is to calculate the total number of valence electrons for the Lewis structure. You do this by summing the valence electrons of each atom in the molecule. Remember that the number of valence electrons for any main group element is its lettered group number in the periodic table. For example, carbon is in group 4A, so it has 4 valence electrons. Hydrogen is in group 1A, so it has 1 valence electron. And oxygen is in group 6A, so it has 6 valence electrons. That means that for H2CO, the total number of valence electrons for the Lewis structure is 4 from carbon, plus 6 from oxygen, plus 2 times 1 from the two hydrogen atoms, for a total of 12. Now, distribute the electrons among the atoms to give octets, or duets for hydrogen, to all atoms. Distribute the electrons in this order. Bonds first, put 2 electrons between each pair of atoms. Terminal atoms next. Give each non-hydrogen terminal atom an octet by placing the electrons as dots around the atom. Central or interior atoms last. So, for H2CO, you first put 2 electrons between each pair of atoms using 6 of the 12 electrons. Then you add 3 lone pairs to the oxygen atom to give it an octet. You have now used all 12 of the electrons, but carbon still lacks an octet. The fourth step applies to cases where some of the atoms in the Lewis structure that you have drawn so far lack octets. If that is the case, then form double or triple bonds as necessary to give those atoms octets. Do this by moving a lone electron pair from a terminal atom into the bonding region with the central atom. Since the structure for H2CO lacks an octet on carbon, move 1 electron pair from the oxygen atom to the bonding region with carbon. Now, all of the atoms have octets and the Lewis structure is complete. Often you can draw the Lewis structure with lines to represent bonding electron pairs. Using this notation, the Lewis structure for H2CO looks like this. All right, here's a practice question for you. Write a Lewis structure for CO2, carbon dioxide. Which structure is correct? A, B, C, or D?
you guys want to go with A? Oh, hang on a minute. It's not letting me choose anything. Go back. Oh, some people say D. I'll put an A because most people are saying A. I mean, I know what the answer is, but I'm going to go with what you guys say.
The correct answer is D. Carbon has to be the central atom because it is less electronegative than oxygen. The structure must have exactly 16 electrons.
All right. So there's one other video in here that I want you to watch. Goodness gracious. I'll show you guys how to tell for sure in just a second. Let's see. Go back one. was 4, 4. Okay. So this one is more, I meant to show you this one first because it's like more basic, but I'll show it to you now. So,
Hello and welcome back. In this video, we
oh, hang on. I want to make sure I'm actually sharing it. No, I'm not. Okay. That would help. There we go.
will have a first look at the Lewis model for chemical bonding. The Lewis model is a theory that helps us to understand how atoms combine to form molecules. This model helps explain why some combination of atoms form stable molecules while others do not. For example, the Lewis model predicts that a stable compound between hydrogen and oxygen is H2O and not H3O. The Lewis model focuses on valence electrons since they are most important in bonding and represents them with dots within a Lewis symbol. For example, the electron configuration of oxygen is 1s2, 2s2, 2p4. Oxygen has 6 valence electrons, so the Lewis symbol for oxygen has 6 dots, representing the 6 valence electrons. The dots are arranged around the symbol with a maximum of 2 dots per side. The Lewis symbol for all the period 2 elements look like this. Notice that the number of dots is equal to the number of valence electrons for each element. Notice also that an atom with 8 valence electrons, which is a particularly stable electron configuration because it has a full outer principal level, is easily spotted because it has 8 dots, which is called an octet. Helium is a bit of an exception. It has 2 valence electrons, which are paired together in its Lewis symbol. Since the 2 valence electrons represent a full outer principal energy level, the n equal 1 level, we call the 2 electrons a duet, which is the equivalent of an octet. In the Lewis model, atoms transfer or share electrons to get a stable electron configuration, which, for most elements, is an octet. For example, some elements, such as chlorine, tend to bond with themselves to form diatomic molecules. The Lewis model accounts for this behavior. The Lewis symbol for chlorine has 7 dots. If 2 chlorine atoms pair together, they can share 2 electrons. The shared electrons count towards the octet of both atoms, so now both chlorine atoms have an octet. The shared electron pair is called a bonding pair, and it is the chemical bond. Electron pairs that are not shared between atoms are called lone pairs. Bonding pair electrons are often symbolized with a dash. The overall diagram for a molecule is called a Lewis structure. Let's look at one more Lewis structure, that for water. The Lewis symbol for hydrogen has 1 dot, and the one for oxygen has 6 dots. We can draw a stable Lewis structure for water by combining 2 hydrogen atoms and 1 oxygen atom. In this structure, each hydrogen atom has a duet, which is a stable configuration for hydrogen, like it is for helium, and oxygen has an octet. This structure explains why water is H2O and not some other combination of atoms. How many lone pairs are in the Lewis structure for water? A, 1, B, 2, C, 3, or D, 4?
2. All right. Let me put in 2.
The correct answer is B, 2.
All right. So now I'm going to go over some of the rules and kind of show you how to do a Lewis dot structure. So let me drag this over to the other one. It'll be just a second. All right. Drag this over here. All right. So temporarily, I'll have a hard time seeing the chat. So just give me a couple of minutes and then I'll be able to see the chat again. I don't know why, like it won't let me. Anyway, okay. So for, let's see, I'm going to pull up a periodic table on my other computer so I can come up with some ideas. All right, come on. I'm just talking to my computer. All right. Okay. So the first thing that you have to do is count the valence electrons. So let's say we were going to draw CH4. Then we would count the valence electrons. To figure out the number of valence electrons, it's going to be the same number of valence electrons as the group. So assuming we're using the AB numbering system. So the AB numbering system looks kind of like this. Etc. till the end is like 8A. Right? So whatever group it's in, that's how many valence electrons it has. So looking at carbon is here, so it's in group 4, and H is over here, so it's in group 1. So carbon equals 4, hydrogen equals 1 times 4, because we have 4 of them. And so that's 4. So we have a total of 8 valence electrons. So the next step is to figure out what the central atom is. And that's going to be the least electronegative. Most of the time they put the least electronegative one first. So in this case, they put carbon first, and it's least electronegative. I can tell it's less electronegative. Well, not necessarily that it's least electronegative. Normally, it's the one that's least electronegative. Technically, hydrogen, in this case, is less electronegative. But carbon can make 4 different bonds. Hydrogen can only make 1 bond. So hydrogen can't have more than 2 electrons. So that would be putting carbon in the middle. We're going to form the bonds. Right? Now we're going to count up how many bonds we used. Let's see. For the transition metals, we're not going to have to guess on the number of valence electrons, but to figure out the valence electrons for transition metal, you have to write out their electron configuration and count up how many electrons are in the highest n level. All right, so in this case, each line represents 2 electrons. So we have 4 lines. Carbon's in the middle in this case because hydrogen can't have more than 1 bond, but carbon can. So for example, it couldn't go like this because this hydrogen has too many bonds. So it can only form 1 of those bonds. So the hydrogens can't be in the middle here. All right, so we've got a total of 8 that we've used so far. So we're going to subtract the used electrons. So we've used 8, so we're going to subtract 8. So we don't have any valence electrons left. So we're going to make sure the central atom has an octet. An octet just means 8 electrons. So counting around carbon, we've got 2, 4, 6, 8. So in this case, we're finished because carbon has an octet. All of our electrons are used. If we got to the very end, like everything had an octet, and we still had leftover electrons, we'd put them on the central atom, but we don't in this case. And we probably won't get to that until we get to the exceptions for octet rules, which is like 4, 6, I think. All right, anybody need a second on this? Oh, now I can see my chat again. Let's see. All right, I think people are saying no. Okay, all good. All right, how come beginning you multiplied hydrogen? Okay, that makes sense. Because we had CH4. So that would be like carbon, hydrogen, 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 hydrogen. So that would be 4, 1, 1, 1, 1. So because there are 4 hydrogens, I just took 1 and multiplied it by 4. Make sense? Okay, good. All right, so let's do carbon dioxide. So carbon dioxide has double bonds in it. So we're going to get to we're going to get to what happens if the central atom does not have an octet. Right? So we have carbon dioxide. The first thing to do is count up how many valence electrons we have. All right, we're going to need carbon and oxygen. Carbon is in group 4, so it has 4 valence electrons. That is group 4A. Oxygen's in group 6A, so it has 6 valence electrons. There are 2 oxygens, so we're going to multiply that by 2. 6 times 2 is 12, plus 4 is 16. Oh, cool. Reba's helped me out. Cool. All right, so which one do you think goes in the middle, the carbon or one of the oxygens? The carbon. It's less electronegative. So if you're looking for it on the periodic table, you get carbon here and oxygen here. So they get more electronegative as they go this way. So the ones on that side are less electronegative. So that's less. Also, it comes first, and usually they put the less electronegative one first. So we're going to put carbon in the middle and connect the 2 oxygen. All right. Let's see. Oh no, least electronegative. All right, so now we're going to count up how many we've used. So how many have we used? 4. Yep. We're going to subtract them, see how many we have left. We have 12 left. So the next thing to do when you don't have hydrogen on the outside is to fill in the octets on them. So is hydrogen more electronegative than carbon? Hydrogen is not. The reason we put carbon in the middle in the last case, even though it's not less electronegative, is because hydrogen is an exception and it can only make 1 bond. So when you see a hydrogen, that's the most it can do. So it couldn't ever be in the middle, because to be in the middle, it'd have to have 1 on each side or something, and it couldn't. It could only have 1. How did we use 4? That's a good question. Each line represents 2 electrons. All right, so it's a total of 4. Yep. All right. So the next thing to do is make sure the outside atoms have an octet. Except hydrogen. All right, hydrogen can't do that. All right, so we have 12 left. So we do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right, and then I'm going to count the electrons around carbon and see if I have 8. So an octet. So it's 1, 2, 3, 4. So I only have 4. All right. Now, also I skipped a step where we've got to count up how many we've used now that, so we used 4 to start with, and then now we have 2 more, 4, 6, 8, 10, 12. So we don't have any extra electrons to put on carbon to make an octet. So we're going to borrow some. We're going to borrow them as equally as we possibly can. So for example, I'm going to take these 2 electrons and I'm going to put them down there. So our structure is going to look like this now. So I want to see again if carbon has an octet. So what do you think? Does carbon have an octet yet? Correct. It just has 6 because each line is 2 electrons. Has 3 lines, so that would be 3 times 2 is 6. So it needs 2 more. So the question is, do I add them from here or do I add them from here? And so we're going to take from the other side, right? Because we want it to be as even as possible, especially when the atoms on either side are identical. So we're going to borrow 2 more. And it really doesn't matter like if I chose to borrow the ones on the end or the ones on the bottom. I just need to take 2. All right, so our final structure is like this. And it doesn't matter where I put these electron pairs. For example, I could have done that, or I could have done that. And it doesn't make any difference. I just want to make sure that I have the correct number and that they're in pairs if at all possible. All right. So let's see. Trying to think of a... Okay, I got one for you guys to try. Does anybody need a second on this page? Let's see. So the O and C have to touch. Yes. And they're touching by... Oh, wait. No, I screwed that up. Hang on. There should have been lines there. That was a good question. I'm glad you asked me that. Okay. This is what they should look like. They should always have 2 lines, right? I thought you meant do they touch by having lines or are they sharing, but I just drew it crazy. All right. Yeah. Sorry about that. All right. Cool. All right. So I want you guys to try this one.